Okay, so last class we were discussing about control of the EVSM motor. There we have learned two methods. One is this is current control, and then second one is that if you want to make the speed control, speed control. This we learn how to make the torque control and how to make the speed control of the EVSM motor. Similar thing is applicable for the DC motor also, DC motor in all the similar situations. Then after we come to the case that here, like you see that whether we are making a voltage speed control or current control, whatever we are doing, a term this PI is coming. So intention is that like how to calculate this PI parameters of the PI control. So this is our objective for today. Let's go ahead. So everywhere we have to calculate it. Then I tried to explain that what exactly the PI controller do. So basically if you see a PID controller, then you find Kp, the constants which are there are Kp, Ki and Kd. So basically we need to find out these values. Okay. So here you see that the three portions, sections of this controller is there. One is proportional. Intention is that whatever the error will be there, it will magnify it and accordingly the action will be taken. Second thing is that integral part. So this integral part, so this is proportional is responsible for the increase in the gain. This integral part reduces your steady state error. How it reduces, I explained you here. You see that I gave you an example. Suppose that in steady state you are reaching to this value like here. So this value is called steady state error. So we can write ESS, steady state error. So with the integral action, what happens that when you integrate the error, then it becomes like a ramp. Okay, and then you are able to reach to the your steady state value. It reduces the steady state error. So not only it reduces your steady state error, but it also improves the settling time. Settling time is what? Like you see that here, this will be an envelope. This will be an envelope. So when the response, your response settles down to an envelope of let's say 2% or 5%, what you want. Let's say that we say that this is an envelope of 2%. So when your response lies between, settle down, and lies between that 2% of envelope, okay, then we say that this settle. Okay. Sometimes we say 5% of. So this is called settling time. So what will be the settling time? Time from here to here, it will be your settling time. TSS. This will be the settling time. So that integral control settle down reduces this. Okay. Settling time also steady state settling time. And this differential, what it does, it basically improves the response, that rise time, like what you see that. It can increase or decrease. It's obvious that it is going to affect the slope because this is the slope. So this is the responsibility what is there. So what today we are going to do is that we have to know that what are the values of this Kp, Ki. So for us, for our purpose, only PI controller is sufficient. Okay, so let us go ahead. So please see this one. You remember that we have represented our BLDC motor like this. Clear? So here the situation is that BLDC or not only this BLDC motor, any motor, you can three-phase motor, you can represent by 3 RLE loads connected. Okay, in star here. If the winding is star, if the winding will be delta, then you will have to make delta connection. So present is any star connection. Okay, RLE load. And so these voltages A, B and C, these are applied with respect to what? These voltages are applied with respect to what? You see that it's the negative terminal of the battery with respect to them. And these voltages can be what? Terminal voltages can be delta, VDC or 0. This I explained to you all. Okay. So this is the case you see. The voltages. So we start our model. What is our intention? Our intention is to ensure a proper application of the phase to neutral voltage, so that we should be able to inject appropriate current, and the current should be synchronized with the flat top portion of the battery. This is our requirement. So what we will do, Intention is what? We have a back EMF. Okay, let's go ahead. Phase to neutral voltage means I am talking about this one. So we want to ensure control this one. Okay, only one leg we are considering, one phase we are considering, where we have to inject a current IA. And this IA is coming from where? Indirectly we are going to control through the DC link. This is clear? Okay. Let's go ahead. So let us consider one of the phase of the BLDC motor. So one of the phase of the BLDC motor is, can I write here? Development of motor model. Okay, motor model. So please see here that we have one of the phase winding we consider, one of the phase you consider, this is R, this is L, and this is E. And this point was our neutral point. This is EA, and the back EMF was trapezoidal in nature. Okay, this is trapezoidal in nature. This is your R, this is your L. And where is the negative terminal of the battery? Let's say this O is the negative terminal of the battery. With respect to what we are measuring the voltages? We are measuring the voltages with respect to negative terminal of the battery. This is phase A. So this voltage is what? This is BAO, which can be delta VDC or it can be 0, depending upon from whether the upper switch is connected or the lower switch is connected. Clear? Now, then next voltage is what? This one. This is VNO. Voltage of the neutral point. Clear? VNO. Then we have the current which is flowing through this. The phase current is IA. Okay, we have VO, VNO and IA. And what is this voltage? This voltage is VAN. Okay, what is VAN? VAN is BAO minus VN. Okay, VAN equal to BAO minus VNO. Okay, so we write KVL for this. See how I write KVL? So writing KVL, Kirchhoff's law, because you are at present writing the equation of dynamics of the current here, because we have to control the current. Okay, so this is called equation of dynamics of the current. So what is the current flowing? So please start from this point. This is rising voltage. Okay, this is rising voltage, so it is BAO. Then we are moving in the direction of current, so it is minus IAR. Then inductor is there, so there will drop in potential, minus L dIA over dt. Then there is a drop in potential, minus EA. Then again there is a drop in potential, minus VNO. This is equal to 0. Okay. So please see that BAO minus VNO is what? BAO minus VNO minus EA, that is equal to, we are bringing it to the right side, IAR plus L dIA over dt. So remember that what is BAO minus VNO? This is phase to neutral voltage, VAN. Similarly, you can write down the equation for B phase, C phase like this one. Okay. So can I write here? BAN minus EA equal to IAR plus L dIA over dt. Let's say give this equation 1. Now please observe this equation. This is BAO minus BNO minus EA equal to this. Similarly, we can write for other phases also. So at present that is not the part of our modeling, but let me write those equations also. So this is for BAO minus BNO minus EA, sorry this one is equal to IAR plus LDIA over DT. Similarly, BBO minus BNO minus EB equal to IBR plus L. So you see that all these equations, what I am writing, those are equation of dynamics of the current which is flowing through each of the phase of the motor. Okay. Is it possible that you can add all this? For each of the fields, just add all of them. What it will be? It is BAO plus BBO plus BCO. It will be there. Can I write it like this? VAO. Can I write it like this? It is AO plus BBO plus BCO. Okay. Then it will be what? 1, 2, 3, 3 times VNO. Then minus, you see that EA plus EB plus EC. So can we write it like this? EA. This summation EA means EA plus EB plus EC. Okay. Then equal to, this is R summation IA plus L D over DT summation when I write summation IA means IA plus IB plus IC. You remember that what is summation IA is IA plus IB plus IC. You please observe that we have this star connection here in the circuit. This one is a star connection. So sum of all the currents meeting at this particular node IA plus IB plus IC. This is equal to what? 0. Kirchhoff's current law. Okay. So this part is basically here you see that summation IA is equal to 0. So what we are left with? This is 0, this is 0. So we are left with just summation BAO minus summation EB is equal divided by 3 equal to VNO. Okay. So you got to know that how this VNO is going to change. So VNO is sum of BAO plus BBO plus BCO minus EA plus EB plus EC. This is what the neutral point is there, and any dynamics of the neutral point affects the dynamics of the motor also. But you just remember all this, rest you forget about it. You don't have to think more about it. Okay, so come to our actual situation here, VAN minus EA like this one. And you remember that we have studied Laplace transform and we have also explained you something. So can we take the Laplace transform of this? Now we are to our actual agenda. This is about the relationship between neutral point. Actual agenda, taking the Laplace transform. Taking Laplace transform. Okay, so what it will become? It will become VANS minus EAS equal to, क्या प्रॉब्लम है आपका? Yes, you are coming first time? नहीं, आपके आगे के बगल में बोल रहा हूँ मैं. पहली बार आप आए हैं तो उनको क्यों डिस्टर्ब कर रहे हैं? Why you are disturbing him? How much is your percentage of attendance? What is your name? Huh? 61. 61 कितना आपका परसेंटेज? 50% है, हाँ 55% है। तो आप उनको डिस्कस करने आएंगे अपने यूनिट से लिया है to don't disturb me, okay? Because he is, I think, he comes regularly. So this is IAS, then it is R, rather I should write complete, R, and this is L. You remember that dx over dt, what we have written, S excess. So similarly we can write here S L IAS, okay? So you can see here that we can write IAS is equal to, means we are in a position to find out what is the can we write it like this? Okay, so let me bring this to another page. This is what we are doing is called modeling. Modeling is nothing but writing the equation of dynamics of the system. Okay, and then use the tools to solve it. This is the tool which is helping us to solve our equation of dynamics. That was the differential equation. So this is the equation. So can we rewrite it, rearrange it like this as you see that this is VAN minus EAS. From here I am taking out L, so it is 1 by L S plus R by L. Can we write it like this? Or just a moment, rather not L, I take out R. This is S tau E plus 1. This tau E is not, you see that this tau E is what? Basically L by R. If you take R, so here it will be L by R. Clear? This L by R is called electrical time constant. Clear? Electrical time constant. Time constant of this electrical circuit. Time constant. So this is done. So can we represent it in the form of block diagram? That here input is BANS plus minus the back EMF EAS. Okay, then it is 1 by R 1 plus S tau E. So output we are getting is the current for phase A. If you want to write for all the phases, then you can write for all the phases. So second page VBN minus VBNS minus EBS it will be 1 by R plus 1 plus S tau for phase B. Similarly for 3 will be there. Okay, all the 3 phases will be there. Clear? Now, so this is electrical part. Now next we know that the torque of the motor torque is given by what? Motor torque is given by torque equal to twice KI. I is the DC link current. Okay? I is the DC link current and this IA is equal to DC link current. At a time only 2 phases are conducting. So whatever the DC link current is there, same current will go through the phase. So it is IA. Clear? You can write here in small. Later on you can, when you take the, so Laplace, if you take the Laplace transform, it will become what? TS equal to 2K IAS. Okay, so from here you see that you know IAS. So is it not possible that because you know IAS, so this IAS will be given with a multiplied with again 2k, where k is what? Back EMF constant or torque constant of the motor. This is equal to torque, motor torque. K is back EMF oblique torque constant. Okay. So torque is also known to you. Please see that one more. So this is torque, it is getting converted. So one more relationship is there. One is what? Between the back EMF and the motor speed. Back EMF and the motor speed. So the equation is what? You please see that back EMF A is equal to K omega M. Electrical part is done. Now we are going towards the mechanical part. We have to relate the electromechanical system. This is electromechanical system. Okay? E equal to K omega M. So remember that your torque is something like this. This is something like this. We are measuring from here in our discussion always. This is one complete period. So this value, what you are observing, is flat value Ek omega M, the flat value. Clear? This is zero value. This is 2 pi by 3. Then this is, you can write here 2 pi by 3. This is 3 pi by 3. This one is 4 pi by 3. This one is 5 pi by 3, and this one is 6 pi by 3. 2 pi means 0 to 2 pi, complete cycle we have taught. It is not good to write like this, rather you write like this: 0 pi by 3, 2 pi by 3, then here 3 pi by 3, this is 4 pi by 3, this is 5 pi by 3, and this one is 2 pi up till this point, here to here. Okay, and this value, what you are rising, this is plus E and this one is minus E. So this is what we are talking about. If it is for phase A, then it is E equal to Q omega M. If it is phase B, then the flat portion will be K omega M, again for the phase B also. So this is the situation. So if we take the Laplace transform of this one, it will become what? EAS is equal to K times omega MS. So you have what? Then actually this was not required at present. We could have found later on. Now this electrical dynamics is over. Okay? Electrical dynamics is over. Now please you remember that suppose that you are having a motor. Let's say that this is a motor. For an example, this is a motor. Rather not to place like this. This is a motor. This is coupled with a shaft. Okay, and here you are having a load. Here you are having load. So motor is producing a torque T, and the load torque is, let's say, TL. Okay, load torque is TL, and then this is rotating at the speed of omega M. Then what is the relationship between this? Tm. Okay, minus TL equal to J d omega M over dt plus b omega M. You remember you have done so many things times like this. J is the moment of inertia, and this moment of inertia is what? All the inertia including the load refer to the motor side. Okay, this is J what we are saying. You look from the motor side, calculate all the values. Okay. Then B is what? Coefficient of viscous friction. Viscous friction B. This B is omega. And this B is also referred to the motor side. Everything is referred to the motor side. Done? So you see that now we have, this is called mechanical dynamics. Nickel dynamics. Okay, means dynamics of mechanical part. So we are able to see the dynamics of the speed basically. There we have seen the dynamics of the current. It is clear? Okay. So now let me copy it again to the another page. There we will go ahead further. Now again take the Laplace transform of this part. So we can taking the Laplace transform. Please remember that Laplace transform is a tool which helps us in solving our differential equations in time domain. So this is what, again take the Laplace transform, so it will become TMS minus, okay, sorry, I have written here Tm now. So we can write here that this is motor torque. It is good to write. This is motor torque, okay, to represent motor torque. This is Tm. This is motor torque. Tm minus this is load torque is equal to, this is what, d omega over dt is S omega ms. So this is Sj omega ms, then plus b omega ms. Okay. So here you can again rewrite it like it is b plus Sj omega ms. So omega ms is equal to what? Tms minus TLS into 1 by b plus s. So here you take out b. Okay, you take out b. So what will be the situation here? We can write it like 1 by b 1 plus tau ms, okay, tau ms Tms minus TLS, where Tm is what? J by B. This is called mechanical time constant. So here you see that here we can again draw the diagram, block diagram. You remember that we have calculated the TMS. Okay, so TMS is coming from there. TMS, then TMS plus minus TLS load torque, then multiplied by one by B plus 1 plus tau ms. Here what we will be getting is speed. Okay, this is the speed as an output we got. And remember, just before we have derived an expression which is relating the speed of the machine with back EMF. Means now from mechanical side you have to go back to the electrical side. Electrical side, then we get the motor torque. So this is what motor torque is done. So this motor torque will drive your load. Okay, this will drive your load, and finally you will get the speed. So now you have to relate this speed with the electrical quantity, so that you will make the complete closed loop. So what is that relationship? This one. So we know that here that EA is equal to K omega m, and so EAS is equal to K times omega ms. Okay, so you have omega ms, so we can here complete our diagram as input is omega ms multiplied by K. So we are going to get the back EMF, EAS. So you see that we started from where and we reached to where. So now we have to combine all these blocks. What we have obtained? This block, then this block and this block. So let us start combining it. So we from where we started? We started from VANS, then it was plus minus EAS. Then what we have placed? You remember? It was 1 by R plus 1 plus S tau E electrical. What was the output? It was the current. Okay. Then we multiplied it with the gain 2K. What the output we got? Motor torque. Okay. Motor torque we got. Then motor torque is compared with load torque. Okay. Load torque. Then load torque. And what was the output here? Tm minus TL. Again we had a block. And what was that block? 1 by B 1 plus S tau M. Okay. Then we got here speed of the motor. Done. And then this speed of the motor was multiplied with what? A constant K. Okay. To get the back here. So this is called motor model. Okay. S domain. Okay. So this is for only one phase. Please remember. Okay. This is for only one phase. So can we write it like this, that we have the motor model for phase A. So this, if you obtain VANS over omega ms, okay, omega ms, this is what? You give the voltage, you get the speed here. Clear? So this is for phase A. So can I write here G, transfer function of the model, if you take the ratio of omega ms over VANS, means if you write omega ms over VANS. So if you write this, this is a transfer function of the model of the motor for phase A. This is transfer function. What is transfer function? It is the ratio of the Laplace transform of output to Laplace transform of input, considering the system is relaxed. This is what it is. Okay. So here you see that what we have given the input, VANS. What the output we got? Omega ms. Similarly, you have the second phase. This is for phase A. Similarly, you can get for the phase C. You give VCNS. Okay? VCNS. Then you will get this. In all the cases, you will be able to get it. Clear? Please remember that here, this is what we are obtaining from here to here. And here one output is also there. What is that? Our consideration is this one. We want to make current control or torque control. So we are taking this current and an output. So here you will get an output also, IAS, if you want to take it. This is IBS and this is ICS. So all the outputs are available. What you want, you do. Okay. What you want, you can realize the control accordingly. If you want to control DC control, then only one block is there. If you want phase current control, these individual phase currents have to be known. Then you will have to consider all the things. Clear? If you have any confusion here, okay, you can segregate up to this part also. VNS minus EB and all those things. But don't worry, we are not interested. So this was just to let you know. So here you see that important is, now again we come to this part. Let me copy it and let me go to the next page. Okay, so this is there. Now what we want? We want to make current control. We want to make current control. Please remember. Okay, this is current control. So what we will do, that this will be the output and rest everything will go into feedback. Okay, everything will go into the feedback. So let me redraw it. This is VANS. Okay, then plus minus. This is EAS. Then here you are having only 1 by R plus 1 plus S tau E, and then output is here IAS current. This is the output, and then multiply here with 2K. Everything is now going to feedback. This is your motor torque. Compare it with load torque. Okay, load torque, and then what we will get and multiply it with the block 1 by B. See, everything is now in the feedback path. Tau M. So this is there. So output is there. It is what? Omega MS. And so multiply it with K. You get back here. See? So you haven't studied control system. Not studied. So you don't know anything about the torque reduction method. We are not also interested in it. But for your information, you can do it by setting this TLS equal to 0. Clear? TLS equal to 0. So you will have a feedback path, this one. So just for your reference, I just want to let you know that suppose that here you give an input RS, okay, just for your reference I am making, and this is the plant GS, and the feedback path is HS. Okay, this is HS, is the feedback path, and let's say this is the output YS. So the overall transfer function in this case will be YS by RS is equal to GS divided by 1 plus GS HS. This is one thing. Okay. Suppose that in your path you see that multiple blocks are in series. For example, this is G1S, this is G2S, and this is G3S. It could be H1, H2, H3 also. Okay. Then this whole can be represented by a block G is equal to, here G we have written, so let's say G dash, another one, G dash S, like this. Okay. And this G dash S will be simply the product of G1S, G2S and G3S. So hope if someone asks you that obtain the transfer function of this current loop, then you can find it. So what is the transfer function for this one? It will be IAS by VANS. Okay, you can find it. Clear? Then while finding the transfer function, you will have to consider TLS equal to Now we are going towards control of this calculation of the PI parameters. Okay, TLS equal to 0, you will have to set, you have to say load torque is equal to 0. So in this case, what will be the value? GS is this, and HS, you see that this is this one and this one. All these are in series. Okay, so just for your reference, I am writing one equation. Okay, I am writing one equation, and later on you think over that. Okay. Okay, sorry. So I am writing here one equation, and so it is IAS by VANS equal to what is GS? Let me know from your table. It is 1 by R, tell me, divided by 1 plus S tau E divided by 1 plus, in feedback path you have H1, H2, H3. What is H1? You see 2K. Okay? 2K. Then that is speed conversion. 1 by V 1 plus S tau M. Then that back EMF K. So this is your HS multiplied by G. 1 plus GS HS, na? So it is 1 by R 1 plus S tau 1 plus S tau E. So you please solve this one and you will get the overall transfer function. Solve it. Okay, my agenda is my time. So you please remember that here we have now a block. What is that block? The block is that we are giving an input here as VANS, and what the output we are getting? IAS. Okay, and what is this? You can write this is the transfer function of the motor in terms of current. Okay, it is current gain what we are saying, GMI I have written. Okay, so what is there? This is GMI for current gain, motor transfer function. This is there. Now what we want? We want to control the current. So what the reference will be? Our reference will be, if you want to control the current, you remember that in the diagram earlier I had written this I reference, IDC reference I had written. Remember the block diagram? कहाँ चला गया? Current reference? It is deleted? Where is that page? I think I got it deleted. Okay, sorry, this one. You see that? This is IDC reference and I feedback, and now we are going to put PI controller, and here delta PWM was given to what? These things. So what the motor model we are talking about? We are talking about the motor model as this one whole. Clear? That is the motor model, and we have to apply some voltage. Based on this delta PWM we have to supply, and what is the value? Delta PWM multiplied by PAN and VDC by 2. You remember that this voltage was VDC by 2? This is VDC by 2. Delta reference what we have calculated. So this is your VA. So VA is what? Delta reference multiplied by VDC. This is your VAN. What we say. So this is coming from where? From the control loop. Okay. So let me write here. that this is going to be plus, minus, and here we are going to put a PI controller. Clear? And what this PI value is? This is KP plus, remember what it was? KI by S. Laplace transform integration is what? You please see here. कहाँ चला गया? Yes, yes, yes. This one. So if you take the Laplace transform of this, you will find what? YS, okay, equal to KP ES plus ERS, na? Plus KI by S, because integration is 1 by S, okay, plus SKD, so ERS I will have to write here, and here also ERS I will have to write. So it is KP plus KI by S plus KD. This is ERS. So what is the transfer function of your error? ERS, sorry, output is Y, na? KP plus KI by S plus KD. This is what it is, and I am writing this one there. Clear? And KI is what? You remember that there is a relationship between KI and KP. It is KP by integral time constant. Similarly, KD is equal to tau D multiplied by KP. This is the relationship. This is the relationship. Okay? So here you see that we have written KIS is equal to, you can take out KP 1 plus 1 by tau IS. So this is the transfer function of PI controller. Clear? Done. So okay, you will solve in a very complex way, then you will solve this, and then further you will multiply g1 g2, then again you will use this formula to further solve it. It is a very complex process. Okay, we don't do that. Okay, rather one trick we use here. What is that trick? Please let me copy this part. Okay, let me copy this part once again to the next page. Now we are talking about calculation of PI, KP, KI values. Okay, KP, KI values. Now please note one thing very important here. We have here two systems. One is mechanical system and another one is electrical system. Mechanical system is what we are getting from the back, is related with the back EMF. So here you are having a back EMF. Here you are having a back EMF. this back EMF. This is what? It's the back EMF. Okay. Let's say for phase A. And what you are willing to control is the current. Which is synchronized with the flat portion of the back EMF. Okay. So please remember that the dynamics of the current is much faster than the dynamics of the back EMF. Please observe here. This is your current. You have to control this current much faster than the back EMF. Okay, much faster. So what we do, that if you read the book by Ogata, then you will find there that it says that suppose that you have a dynamics of a system which is much slower. EA dynamics is very much slower than the back the current. So what we do, that we can neglect the dynamics of this part. Okay, this part dynamics is neglected. Okay, so you are left with only VANS. This part is not there, so you are left with only 1 by R plus S tau E equal to IAS. So your G motor IS, that is IAS by VANS, is equal to 1 by R plus 1 plus S tau. So I request you that please substitute this one in your previous equation, here, and calculate the overall transfer. So you will get IAS over I references. So you need to calculate IAS over I reference S. Okay, I reference S. Please calculate this. You will have a polynomial second order system. Then we will discuss the next class. So then it will take 10 minutes. Next class we will discuss this. We will discuss the simulation also. So this is called motor modeling. Okay, and the control. If you want to go for the speed control, take the reference as the speed. If you want to make the current control, take the feedback as the current and current reference. Compare this with current. What you want, you will that. So next class we will discuss further. I am stopping here.